Okay, so these were the class notes from last time, and we looked at the Gaussian filter and box filter, right? So one point that I forgot to mention last time is this normalization. Um, we need to normalize. Normalize means what? You just divide that filter by the average of the sum of the average of all the elements in that filter. Okay, so this is done for two reasons. One reason is that so if you have a region of constant intensity, which means so in this image, okay, if you're looking at the background gray, okay, so these are areas of constant intensity. And then when the image is, so this is the original image, right? And the background is all this gray. This is constant intensity area. Even in the filtered image, we are seeing the same intensity in the background, correct? So all these filterings are not changing the, or even in within this letter. Okay, this is also area of constant intensity. All these pixels have the same intensity, and that same intensity is retained. Okay, so to retain these intensities in areas of constant intensity, you have to take this normalizing. Otherwise, what will happen is, well, you can imagine what will happen, right? When you take the sum of all these and put it in the center pixel, if the original, suppose you had 1 everywhere, okay, then that in the center pixel now you're replacing it with 9 instead of 1. Okay, so the intensity of that pixel changes. Okay, so to avoid this change in intensity, this normalizing factor is multiplied to the box filter. Okay, or in fact any filter that we will see. Normalization also prevents bias. Bias means uh, essentially this, that the intensity values of the pixels in the original and the filter. So sorry, original is here. Original and filtered image. Okay, these pixel values will be the same. There won't be any additional terms in there. Okay, so for these two reasons, normalizing has to be done, and so I added these normalizing factors in front of the box filters. There should be one here also. Yeah, it's here actually. This normalizing factor. Okay. Now, when looking at this Gaussian filter, there are one or two things that need to be taken into consideration. Okay, one is the action of this Gaussian filter. So you know that the Gaussian filter is actually defined in this way, and if you think of this as a function of two variables, this is a continuous function of two variables. Okay, so if you plot this, you will have a surface like this. Okay, but what is being done when you look at just 3 by 3 Gaussian filter is that at the center, what we are doing here is sampling this surface. Okay, you are sampling this surface with this kind of box. Okay, so this box in the XY plane. Okay, so at these coordinates, you are sampling the surface of the Gaussian. And exactly the values on the surface that you get by sampling are the entries of this box filter, of this Gaussian filter. Okay. So for example, when mu is 1 and sigma is 1, then at 0, 0, okay, the value of GST is 1. And that is why here we have 1 at 0, 0, that position. Okay. Then position 0, 1 is whatever on this. And the thing with the Gaussian, as you know, it is going to be circularly symmetric, right? So this is the same thing that we see here. Okay, so if you take the level surface, okay, then you will have a circle. Every level surface is a circle. Okay, and so that is reflected in the nature of the filter also. Okay, this is what I was saying last time, that along a circle the values will be the same. Okay, so these are some basic things to notice for a Gaussian. Then there are two or three more important properties of a Gaussian filter that make these sort of unique, okay, and irreplaceable. So Gaussian filters have the following important properties. One, they are much preferred over box filters. Okay, so Gaussian filters are preferred over box filters for the following reason. Because they do not introduce what is called as directional filtering artifacts. Okay, they do not introduce blur or the artifacts that come from filtering. Okay, what this means is that, well, if you apply this box filter, for example, So in the homework, as I said, there will be an example where you will be able to look at the jagged edges closely, okay, and the differences that happen when you apply a box filter and Gaussian filter. So what happens when you apply a box filter is that because of the nature of this filter, okay, at the edges or and at the contours of these objects, you will have corners, okay, so you will have shapes that look sort of like this, okay, so there will be a directional blur, okay, so there will be corners like this that appear at the edges or contours of objects, okay, and that is because the way the box filter is designed. On the other hand, for a Gaussian filter, that does not happen. For a Gaussian filter, that doesn't happen because of its symmetry in this way. Okay, because it is circularly symmetric, you don't see those jagged edges. In fact, the blurring is smoother. Okay, so they do not introduce directional blur, and the blurring is smoother. Okay, so that is the reason, one of the reasons, basic reasons to prefer. However, box filters are very easy to design, so if you just want to do a quick experimentation, you can go with the box filter. Okay, you're trying out some various things and you want to quickly see how blurring will look like, you can because box filter you just fill ones, right, make a simple array of numbers, whereas Gaussian filter will take some calculation. Okay, however, nowadays you don't have to do any of that, OpenCV has functions for all of it. But yeah, anyway, the other thing is that so this point itself, that the blurring is smooth, is also termed as being isotropic. Okay, so this is also termed as uh, uh, isotropic kernel. Okay. Sorry, isotropic kernel. Okay, isotropic kernel means that a kernel whose action is independent of the orientation. Okay, it does not. So when you don't have you don't get artifacts like this because these are not sort of the preferred directions or anything. Okay, the kernel is circularly symmetric, and so there is no preferred orientation. So this is independent of orientation. Another way of looking at it is simply, well, if you rotate this kernel through any angle, okay, I mean, well, of course, through 90 degrees or 180, those kind of angles, you will get back the same kernel. Okay, so such a kernel is called isotropic. So the isotropic kernel, that is, their response or the response is independent orientation. Okay, that is one thing. The another important thing about Gaussian kernels is that Gaussian kernels are also separable. So box filters are also separable, right? So what is so great? So it has been proved that Gaussian kernels are the only isotropic kernels or only circularly symmetric kernels that are also separable. Okay, and that makes Gaussian kernels very important. Okay. Moreover, with this separability, we have a nice property, that is the mean and standard deviation. So separable means what? It can be broken up into two one-dimensional kernels, right? So if you know the mean and deviation, standard deviation for the two one-dimensional kernels, then from that you can calculate the mean and standard deviations for the correlation and the convolution kernel obtained from those two one-dimensional kernels. Okay, so that is one more property of Gaussian kernels. Okay, so they are separable, which means they can be written as the product of two one-dimensional kernels. So suppose G is written as a product of two one-dimensional kernels, say small f and small g. Okay, then the product and convolution I should have said this first. I should have said that product of Gaussian kernels, product in the sense either correlation or convolution of Gaussian kernels is also Gaussian. Okay, so I should have uh, added that point first. Yeah, the correlation and convolution. So these are just two kinds of products, we can think of it that way, of two Gaussian kernels is Gaussian. And um, so suppose now you have separated G as a product of two one-dimensional kernels f, small f and small g, then well, small f and small g, suppose the mean and the standard deviation for small f and small g are given by, say, mg, sigma f, sigma g. Then it turns out that for the correlation f cross, yeah, f cross circle g and convolution f star g. So these will also be Gaussian with the mean given by this formula divided by sigma f squared plus sigma g squared. Okay, and similarly the standard deviation for the correlation is given by square root of sigma f squared times sigma g squared divided by sigma f squared plus sigma g squared. Okay, so this will also f circle star g will also be a Gaussian kernel with this mean and standard deviation, and the convolution of these two will also be Gaussian with. Okay, so I'm not proving all this, but it is not too difficult to prove either. Okay, but this is so these are some of the important properties of Gaussian filters which make them irreplaceable. Okay, so I want to talk about uh, Fourier transforms today a little bit. But there is also the topic of sharpening. So both box filter and the Gaussian kernels are smoothing filters. Okay, and as I mentioned last time, we also want to look at some sharpening filters. And sharpening filters are mostly based on derivatives. Okay, that is the first order derivative filter and the second order or the Laplacian filter. Okay, uh, so these two I will probably either do it in the week after the midterm or I will record and put it up. Okay, because I don't want to spend time on it in class, and moreover I want to move on to frequency domain because there will be some reading assignments before we go ahead. Okay, so I will stop with this for now. Okay, so frequency domain filtering, way it proceeds, okay, is as follows. So you have your image in the spatial domain, which is converted to an image in the frequency domain. Okay, so this is done using the discrete Fourier transform, and then the image is processed in the frequency domain. Okay, whatever filtration or anything that you want to do can be done in the frequency domain, and then the image is again transferred back to the spatial domain using the inverse discrete Fourier transform. Okay, and you can derive conclusions about the image from its the filtering in the frequency domain. Okay, so usually what this looks as follows. So you have the input image fxy, and the output image will take the form. So there will be real. So for now, just forget about this real. Okay, we will come back to it when we look at the formula in detail. So this is going to be, so let me say F inverse. Okay, so this will be the inverse Fourier transform of, so suppose the input image F, you have applied the discrete Fourier transform to it and transferred it to the frequency domain. There we are going to call it capital FU. Okay, so applying a filter to this FUV in the frequency domain will be like multiplying with some HUV, okay, some function in the frequency domain, apply it to or multiply it to FUV. Okay, so this is how the mechanics will be. So you have your original image, you have converted it to the frequency domain. There you have applied some filter HUV. Okay, then you take the inverse Fourier transform of the result. Okay, it's the filtered image, and take the real part of it. So this we'll see when we come to the details. Okay, and that is your output image. Okay, so this is in general how the filtering or frequency domain filtering outlook looks like. Okay, so now let us go to some basics of frequency domain. Okay, so I will go through the highlights of the theory, because this is not the aim of the course to do signal processing. But on the other hand, if you don't understand the main points, then you will not be able to apply it. Okay, so I will try to go through those points that you actually require in applying frequency domain filtering. Okay, for the details, you can either, I will suggest some reading. Okay, I also have some detailed notes that I can post from time to time. And if you have questions, you can ask me. Okay, but otherwise in class, I will not go through all the details. So for the discussion of this entire frequency domain processing, in the beginning at least, we will consider an image. So for this discussion, an image will be considered as a continuous signal. Okay, and always we will think, okay, image is a continuous signal which is being discretized using some kind of sampling. Okay, so with this in mind, we will set up some or look at some basic terminology, and then we will look at sampling. Okay, and then how all this can be taken to the discrete case. Okay, so there is something called as spatial frequencies in image processing. So in general, what does frequency refer to? In general, the word refers to the repetition of something, right? So in general, frequency refers to repetition of a signal. So for example, you can have something like this. Okay, if you think that its function stands for a signal. Okay, so how many times is this peak being repeated? Okay, so in a given time interval. Okay, so that is you can count that as a measure of frequency. Okay, so in image processing, frequency or spatial frequency will refer to the rate of change of pixel intensity in an image. When we say frequency, we mean spatial frequency. The word frequency, so both terms are used. So I'm writing both frequency or spatial frequency. Okay, and how do we visualize these pixel intensities? So if you remember earlier, we use a scan line, right? So you can use a scan line or line profile of an image along a row or a column to generate the intensity profile along that scan line. Correct. So this is how. So suppose you may think of this as an intensity profile at some point along some line. So the intensity profile in general, okay, not exactly like this, but whatever it comes out to be. So we know from analysis in Fourier series that it can be any intensity profile or any continuous signal like this can be written as a combination of sinusoidal signals, okay, such as sine, cosine, okay, or even a combination of non-sinusoidal signals. So I will write that later, but what I mean by sinusoidal signals is something like this. So you can have something like this. Okay, so this you can write as a sum of some sines and cosines. Okay, definitely something like this can be written as a linear combination of sines and cosines. Okay, non-sinusoidal will be something like this. Okay, or if you have something like this. Okay, so these are sinusoidal, non-sinusoidal. It turns out that high frequency components of that intensity profile, high frequency components in an intensity profile correspond to rapidly changing data. So what this means? Changing data. So suppose you have an image and you have scanned it using a line, and at a certain position of the scan line, your intensity profile looks like this. Okay, so this, you can imagine, this is a high frequency component. Okay, the frequency is high over a given time interval. So then this usually corresponds to what could be rapidly changing data in the image. Okay, rapidly changing data means there could be an edge. Okay, so the intensity has changed at that point. Okay, or there could be maybe in the original image there could be lines like this. Okay, so the intensity has gone up, then or whatever, up down, and so on. Okay, so some a presence of something like this, a scan line is here. Okay, then the intensity profile along the scan line is going to be something like this. Okay, and so I mean, these things can be proven more rigorously, but I'm just, as I said, giving you the highlights. So high frequency components correspond to rapidly changing data. On the other hand, low frequency components will correspond to large scale features. Okay, there are some mountains here. Okay, and the color, there is not much change in the color or something. Okay, or if there's even better, you have just one peak. Okay, some snow-capped peak, I don't know. So then if you have this scan line going along here, then you can imagine that in the intensity profile of something like this, you will probably have just something like this, right? The intensity profile might be something of this shape. So then the frequency is low. If you measure over a time interval, the frequency here is low. Okay, so this is what a general way of looking at frequency computation. Okay, but of course we will go into more detail than this. So now let's talk about coordinates. So in the spatial domain, we have coordinates x and y, right? We have coordinates x and y. In the frequency domain, we will have coordinates u and v. Okay, and what these stand for will be clear a bit later when we actually look at the Fourier transform. Okay, so but these are both related to the intensity of the pixels. Okay, so you can, in one dimension at least, this u represents the spatial frequency. Okay, so well, what does this mean? This means that the cycles of unit. So if you have, so say your independent variable is t. Okay, so suppose your independent variable is time, and then you are counting how many peaks are there in this intensity profile. Okay, so then the spatial frequency, that variable, will be measured as cycles per unit of t, right? So how many times this cycle is repeating. So if you decide to look at, say, something like this cycle, how many times this shape repeat? Okay, so that is the measure of the spatial frequency. Okay, uh, and in fact, v is also the same in the other direction. Okay, so these are both nothing but measures of rate of change of intensity. Okay, so these are u and v are or represent the rate of change of intensity. Rate of change of intensity. So these will be the variables that we will use, u and v, for the Fourier domain. Okay. In general, transforms in the frequency domain. Frequency domain does not always mean Fourier domain. Okay, there are other frequency domains also. Okay, so in the most general case, transforms in the frequency domain can be of various types. In the frequency domain, these could be orthogonal, which means sinusoidal. This is just the term, also called as orthogonal transforms, or non-sinusoidal. So Fourier transform is one example of these sinusoidal frequency domain transformations. Okay, so Fourier transform, which uses either the discrete Fourier transform algorithm or the fast Fourier transform algorithm. Okay, this is one example, but there are others also. There is the discrete sine transform. So this is DST, and discrete cosine transform. So I'm mentioning these only because to say that even though we will be focusing on the Fourier transform in this course, there are other frequency domain transformations also possible. Okay. We will not go through all of these because then that's just too much. There are also non-sinusoidal transforms possible. There's something called the Haar transform, Walsh transform, Hadamard transform, and so on. Okay. So frequency transformation can be done in any of these domains or using any of these transforms. But then again, in each case, you need to know the properties of those transforms. Okay, and what is the frequency profile telling you in each of those cases. Okay. Other than these, sinusoidal and non-sinusoidal, there are transforms based on PCA or SVD. Other transforms. So if time permits, we will talk a little bit about this. SVD or PCA transform. Okay. There is something called the KL transform, the Kionen-Luga, I think, transform, which is also quite famous. Okay. Out of all these, we will only look at Fourier domain transforms. Okay. What are applications of all these transformations? Applications of these. So one, and one of the most important ones for us also is that the operation like convolution that we saw earlier, okay, is easier to transform in the is easier to perform in the frequency domain. Okay, because we will see later that this convolution that we saw earlier, the sum of products operation that we do in the spatial domain corresponds to just a multiplication in the Fourier domain. Okay, so it will turn out that so suppose your original image is some m cross n. Okay, so then you will apply the Fourier transform and get some, I should do it this way, small m cross n, capital M cross n here. Okay, so this FUV is m cross n, and then applying a filter to it. Suppose you want to do convolution, will correspond to just point-wise multiplication with another m cross n array. Okay, so it will not be like passing this filter over every pixel and all. It will simply be multiplication by another array, point-wise multiplication. Okay, so you take the image, your original image, transform it to the Fourier domain, apply this simple multiplication and bring it back to the spatial domain, and your filter is applied that way. Okay, which is it requires much less number of computations than doing that convolution process, passing your window or kernel over the entire image pixel by pixel. Okay, so applying convolution is much faster in the frequency domain. Okay, It also gives insights into sampling. How was the sampling process? Okay, so we will see examples of this, how it gives insight into the actual sampling process. So image, remember, we are thinking of it as a continuous signal and it is being sampled discretely on the sensor. Okay, so how was the sampling? It gives insight into that. Okay, it also performs much better at detecting noise. So if the, and not only detecting and then eliminating also, because so if you have an image which in which the noise is all over, okay, but in a pattern. Okay, so suppose you have this image, okay, something, and you have noise in the form of some say lighter pixels going throughout the image like this. Okay, so suppose you have something like this, then in the frequency domain, this noise will appear in certain points. Okay, and then you can apply a filter to just get rid of these, let's say these four intensity or these 4 points, and then bring back, and in the original image these will be, then the noise will be gone. Okay, so what I want to say is that if the noise is in a certain pattern, then it's easier to detect and eliminate in the frequency domain than in the spatial domain. So for example, here if we were performing operations only in the spatial domain, then getting rid of this noise would be difficult. So for example, even if you applied Gaussian blur or anything, okay, the Gaussian blur would in fact blur the entire image, right? And if you don't want to do that, but just get rid of this noise, then the frequency domain uh, filtering is much preferred choice. So I will write down these applications later when I complete these notes. Okay. Another important use of frequency domain transformation is image compression. Okay, so it performs image compression also in a much more efficient way. Okay, so these are some applications. So how much time do we have left? Oh, we have half an hour. So we can start talking about the Fourier transform. First, what we'll do is we'll look at the formula in one dimension, and then I will, for a one-dimensional continuous function, we will state it, and then we'll state it for one-dimensional discrete form. We will see the computation for a small example, and then we will state the form in 2 dimension. Okay, the discrete 2 dimension form. So that that should give you a pretty good idea of uh, what this looks like. So in one dimension, so you consider a continuous function f of x, where this x, okay, just continuous function f of x, where x is a continuous variable. Okay, so let f of u represent its Fourier transform. Okay, where u corresponds to the spatial frequency. Okay, so f of u, the definition of f of u is integral minus infinity to infinity f of x e raised to minus 2 pi I ux dx. Okay, so well, you might recognize from this that this thing is going to be a combination of sines and cosines, right? So in fact, this entire function capital F of u is going to be a combination of sines and cosines. So just to stress that point, let me write this as integral minus infinity to infinity f of x times cosine. That's what this Euler formula gives, right? Cosine 2 pi ux minus I sine 2 pi ux dx. That is capital F of u. Okay, so this capital F is the Fourier transform of small f. The inverse Fourier transform Fourier transform is small fx equal to integral minus infinity to infinity capital F of u times cos. Now there is no minus. Okay, this e raised to minus, that minus will be gone. So this will be cos 2 pi ux plus I sine 2 pi ux dx. Okay, so which in shorthand is e raised to 2 pi I ux dx. So for one variable, these are the formulae for the Fourier transform and the inverse Fourier transform. Okay, and this was for a continuous variable, continuous function of a continuous variable. So now we want to write all this in discrete form because that is the kind of data that we are going to deal with. So in discrete form, the Fourier transform is written as well, your integral will be replaced by summation. Okay, and we will also have this average outside. So 1 over m summation x going from 0 to m minus 1. So this is where the m is fixed now, right? So instead of going from minus infinity to infinity, you're doing this over some interval 0 to m minus 1. F of x e raised to minus 2 pi I u x by m. Okay, which in general is a complex number. So this f of u will be a complex number, of course, you can see. And the inverse DFT is f of x equal to summation capital F of u e raised to 2 pi I ux by m, where u goes from 0 to m minus 1. Okay, so let's do a small example of applying DFT and inverse DFT. Okay, just to get a handle over these ideas. So suppose your fx, the discrete function, is given by 1, 2, 8, 9. Okay, so if nothing is mentioned, what this means is x is taking the values 0, 1, 2, 3. Okay, because that is our x equal to 0 to m minus 1. Okay, so there are these 4 values. X takes values without saying from 0 to whatever, how many ever function values are there. Okay, and this is the given fx. Now let's apply df to this. Okay, from this we know that capital M therefore is 4. There are 4 points, 4 sample points. Okay, so if we apply dft, well, f of u is 1 over m summation, see this formula up here, f of x e raised to minus 2 pi I u x by m, where x goes from 0 to m minus 1. Okay, so we just substitute the terms in this. So for this, let's calculate. So also one other thing to realize from these formula is that, well, the range of x was 0 to m minus 1, then the range of u is also 0 to m minus 1. Okay, so the Fourier variable, okay, or the transform variable will also move over the same range. Okay, so u is also going to have 4 values. Okay, so u will also be from 0 to 3. Okay, so that means we have to calculate f of 0, f of 1, f of 2, f of 3. Okay, and so you can do this very easily now. So this is for f of 0, this is going to be summation x equal to 0 to 3, f of x times e raised to minus 2 pi I, u is 0, x divided by 4, right? So now we'll have e raised to minus 2 pi I 0 x 0. So e raised to 0 there. Okay, and so we are simply doing f0 plus f1 plus f2 plus f3. Okay, so f of 0 is just the sum of these four function values, which comes to 1 plus 2 plus 8 plus 9, which is 20. Let me write that. 1 plus 2 plus 8 plus 9. Okay, so now imagine if this f was an image. Okay, so let's just think of a line in an image. Okay, so what are these then? If f is an image, then these values are the pixel values at these positions, right? And so what is f, capital F of 0 doing? It is just taking a sum of these values, right? So for an image f in 2D later also, this is actually going to be the sum of pixel values. Okay, that is what capital F of 0 will mean. All right. Now we can calculate capital F of 1 in a similar manner. So summation fx e raised to minus 2 pi I 1 x divided by 4, x going from 0 to 3. Okay, so this is going to be, when x is 0, this is f0 and e raised to 0, correct? So times e raised to 0, plus when x is 1, this is f1 times e raised to, so when x is 1, this is going to be e raised to minus 2 pi I by 2, or just minus pi I by 2, correct? Plus f2. So this 2 will cancel with the 4, and then you have sorry, e raised to minus pi I plus f3 times e raised to minus 3 pi I by 4. Okay, so if you compute these values, so this is just f0, e raised to 0 is 1, plus f of 1 was 2, so 1289. So 2 times this e raised to minus pi I by 2, you can check that is minus I. Okay, plus 8 times, you can check that e raised to minus pi I is minus 1. Okay, just, I mean, use the cos and sine form of this, plus 9 times e raised to minus 3 pi I by 4, that comes out to I. Okay, so this will be minus 7 plus 7i, which is a complex number, and that is what we are expecting actually, correct? Because I mean, these kind of terms tell us that capital F is going to be a complex number. So this is f of 1, and so I will leave calculating f of 2 and f of 3 to you. Okay, so you can check that f of 2 comes out to minus 2, and f of 3 computes to minus 7 minus 7. Okay, so this is computation of the discrete Fourier transform for this small function f. Now we can compute the inverse of this, inverse DFT. So this also I'm not going to do all the computations, I'll leave it to you. So this is the formula, summation u goes from 0 to n minus 1, capital F of u times e raised to 2 pi I u x by m. Okay, so for x goes from 0 to 3, right? So we want to do small f of 0, small f1, small f2, small f3. So f of 0 is 1 over 4, just like before. This is just going to be capital F0 plus capital F1 plus capital F at 3. Okay, And you can check that if you do all that, it becomes 1 over 4 multiplied by 4. So this is 1. And this is what we have, right? I mean, that is the expected answer. Okay. So you can check that the expected answers are, sorry, the answers that you get are equal to these expected answers. Okay. So check that f of 1 is 2, f of 3 is 8, and f of 4 is 9. Okay, as it is expected. All right, so this is just a small example of application of DFT and IDFT to discrete data. Okay, and so now let me just write down the formula in 2 dimensions. And this is what we will be actually using. Okay, so if fxy is a m cross n array, then the discrete Fourier transform f, capital F, variables u and v is given by, so this is a generalization of the one dimensional thing only. Okay, you can find more details in the book or some book on Fourier transforms. I will provide a reference to you so that if you need help convincing yourself, then you can look at the reference. So e raised to minus 2 pi I ux by m plus vy by n. Okay, where y goes from 0 to n minus 1, x goes from 0 to m minus 1. This is the discrete Fourier transform in 2 dimension, and the inverse discrete Fourier transform will be analogous. Small fxy given capital FUV is capital FUV e raised to 2 pi I ux by m plus vx by n, where v goes from 0 to n minus 1, u goes from 0 to m minus 1. Okay, so just I mean, you can think of going from the xy variables. Your image is going from xy variables, where it was called f, a domain where the variables are u and v. Okay, and here is your capital F. Okay, we will work more on these kind of or understanding details of this transformation in the next class. Okay. So there are a few things to keep in mind, that this FUV is a complex number, right? So there is a real part and an imaginary part. And that is the real part that was mentioned up here. Where is it? Here. When you want to come back from the frequency domain to the spatial domain, okay, you take the real part of this inverse. Okay, this is the inverse Fourier transform. Right, so you have done filtering here, then you apply the inverse, and then you take the real part of that to get your image values at xy, okay, or pixel values at xy. So this real part is because after you apply the inverse, you will, I mean, this f is going to have a real part and an imaginary part, okay, and well, you'll see in an example. It's better to just look at one example and understand. Okay, so oops. So let me just write this down. FUV is a complex number. So you can write FUV as RUV, the real part, plus iota or I times capital IUV, that is the imaginary part. Okay, then using this, you can compute the magnitude and phase or angle as mod FUV. Well, this I'm sure everybody knows. This is just square root of the real part square plus imaginary part square. So RUV squared plus IUV squared. Okay, and the phase, which we'll denote by phi UV. This is tan inverse of the imaginary part by the real part. Okay. So it turns out that just as you plot FUV, right? So uh, so this UV is going to give you the location in this domain, right? So at this point, you will plot FUV, that intensity, correct? And or that frequency. So similarly, you can also plot magnitude and phase. Okay, so these two can also be plotted. Okay, or these two will also give you. I mean, if you plot them, you will get something of the size m cross n. Okay, with these FUV or FUV mod FUV plotted at those locations. Okay, so this thing is called the magnitude spectrum. Okay, so mod FUV, if you plot, you get what is called as the magnitude spectrum. Okay, and if you plot phi UV, this gives you the phase spectrum. And these will also have, we will also look at these when we want to do image analysis with the filtering. Okay, so both these have uses in analysis, image analysis. So what are the three things? One, you can look at the frequency domain and the frequency transform of it. Then you can also look at the magnitude spectrum of F, and you can look at the phase spectrum of F. Okay, so these are three things that you can look at given an input image small fx1. Okay, and finally, I want to talk about how the DFT can be framed as a matrix operation. Okay, this is useful because if you remember from numerical linear algebra, I had talked about these level 3 blasts, right? As far as possible, all operations should be tried. I mean, one should try to frame operations in an algorithm as level 3 blast operations, which means matrix multiplication operations for efficiency. So the DFT can be framed as a matrix operation as follows. Can be formulated as a matrix operation. So if we, yeah, I'll write the general one and then we can just look at the example that we did above. So suppose y equals, not suppose, it can be formulated as follows. Y equals w times x, where if we let omega m denote the mth root of unity, sorry, omega small m denote the mth root of unity. Okay, which means this is e raised to minus 2 pi I by m. Okay, then if your and then your w will be the matrix omega m0 small m, omega m0 dot dot dot. So that's the first row and the first column. Okay, and then in the from 2 to onwards, you have omega m1, omega m2, omega m m minus 1. And the numbering changes like as follows. Okay, so now this will be omega m2 and the next will be omega m4 and so on. Okay, and this is how it will go on to omega m minus 1. Yeah, so here's the thing. I should have had capital M here because this is going to go on to capital M minus 1. Okay, where capital M is the number of uh, samples, or like in the earlier example, it was 4. Okay, so this is W, and so the discrete Fourier transform therefore can be formulated as this matrix operation with this W. Okay, so if this W is applied to your variable X, then you will get the output Y. Okay, so for example, just to demonstrate this in that one dimensional example that we had done earlier, where fx was 1289, for x values being 0, 1, 2, 3. Okay, your omega, so you omega m would have been omega 4. So this is 4th root of unity. So this is minus I. Okay, and therefore the matrix W in this case will be, well, omega 0 everywhere, so that's just ones. So omega 4 raised to 0, so that's all ones. Okay, and then you will have omega 4 raised to 1 omega 4 square and so on. Okay, so this is going to be minus I, then the square of that, so minus 1, then I, okay, and so on. Then here omega square, so this is minus 1, okay, and then raised to 4 and then raised to 6, so that will be minus 1. Then this will be omega 4 cubed. Okay, so the remaining thing is I, then minus 1, minus 1. So this will be the matrix W. Okay, and so applying DFT to fx, applying DFT to the image, or yeah, okay, image fx is same as applying W to fx. Okay, so you can say that capital F of u is equal to W times f of x, and you can check that this is true. Okay, so this matrix applied to the vector 1, 2, 8, 9. Okay, so W applied to the vector 1, 2, 8, 9. You can check, will give you the vector 20, minus 7, minus 7 plus 7i, minus 2, and minus 7, minus 7. Okay, so this is how DFT can be framed as matrix multiplication, and in fact the inverse is the inverse DFT is taking W inverse. Okay, so you can also check that f of x is this 1 over 4 should not be forgotten, W inverse f of u. Okay, so in this case I have calculated this. W inverse comes out to be well, you have the same terms here. I minus 1 minus I, minus 1, 1 minus 1, minus I, minus 1 I.